Let's talk about fascinating world of computer science, where we will explore the essential building blocks that make computers tick. Our focus will be on three key components: language, memory, and microprocessor, the heart and brain of the machine. Imagine you have a computer, a mysterious black box. Whenever we encounter something unfamiliar, it's crucial to establish a means of communication. Picture this. You are holding number 5. Now, if you want to increase it, simply add 1 and voila, you got a 6. Conversely, if you want to decrease 5, subtract 1, and you have the 4. These two commands, increment and decrement, form part of the language we use to converse with the computer. And guess what? We don't even need to use full words. Abbreviations work just fine for faster communication. Imagine a table like a basic spreadsheet. We've got two cells, let's call them A and B. Now, we want to tell the computer something like, hey, remember the number 5. So we use a command called move. We say move 5 to cell A. And there's more, we can also move another number like 8 to cell B. Instead of saying move every time, we use the abbreviation again. MVI. It stands for move immediate. Fancy term, but all it means is that we are putting a number directly into the cell. Now here's the cool part. We can combine commands. First we move 5 to cell A, then we increment whatever's in there. Think of it like adding a little extra to a cell. And guess what? The result is stored there as well. It's like a secret stash where we keep our data. Let's dive into a practical example. I'll show you a simulation of how this all works in a real-life scenario using the same input data. No need to be a tech wizard, just follow along. Here is a simulator. Let's try move 5 to cell A. And as you can see, it really happened. This particular memory, this particular cell A, is called register. Let's try to increment. And as you can see, we got number 6, exactly as expected. Now we can talk to computers. We got our language, a way to share data, but there's still a big question. Where does the computer store its dictionary of commands, and how does it know what to do with them? The answer lies in a tiny powerhouse called the microprocessor. Think of it as the computer's brain. One crucial part of this microprocessor is arithmetic logic unit, ALU. Sounds fancy, but it's actually pretty simple. Imagine a circuit with two switches, one on the left and one on the right. If both switches are off, no electric current flows and the light stays off. We can describe this situation using binary code 0, 0. Now let's mix things up. If both switches are on, both set to 1, the light turns on. Why? Because the current flows, the circuit is complete, and voila, the light shines. Let's try another. Here's the twist. If only one switch is on, set to 1, the light still turns on. These two circuits are like superheroes in computer science. They even have cool names, AND and OR. They handle logical operations, and you can see their magic in action in the tables below. We've been discussing increments, and here is the twist. Sometimes incrementing is like saying OR 1. Let's take a fresh look at the table. When you add 0 plus 0, you get 0. Adding 1 plus 0 gives you 1. And 0 plus 1 also results in 1. What about 1 plus 1? That's a special case. Let's put it aside for now. Shift your focus to the right side. Imagine we start with the binary number 0010, which represents 2 in decimal. If we add 0001, which is 1, using the OR operation, we got 0011. In good old decimal terms, that's 3. And that fits with our expectations. Incrementing 2 should lead to 3. These clever little things are called logic gates. And guess what? We can build a basic arithmetic unit using them. But here's the real surprise. All those other logical operations, they can be replaced by a single gate called NAND, which stands for not AND. Here is a picture showing AND gate built from NAND gates. And there's this cool chip, the 7400, which serves as an arithmetic unit. Inside is just a bunch of these NAND gates working together. They are like Swiss Army knives of computing, versatile and ready for anything. Here is a simulator of 7400. As you can see from the schematics, there are 14 pins. Let's try to switch 13 and 12. After changing to 1, the output 11 changed to 0. Similarly, 5 and 4 controls 6. Let's summarize. Imagine you got a device, a computer. Now, how do you talk to it? In our case, the language is a bunch of commands. We call these commands instructions. In everyday life, we often use abbreviations or shortcuts for these instructions. But here's the thing, instructions alone aren't sufficient. We also need to exchange data, save it and load it. And guess what? That's where memory comes into play. Now, memory does more than just store data. We'll dive deeper into that in a future video. And finally, the cool part. All those instructions, they are hardwired into the computer's hardware. Specifically, they are etched into the microprocessor or CPU. It's like having a secret recipe book right there in the chip itself. Logical operations, yeah, they're part of that recipe too. That would be all for today. Thank you for watching and see you next time.